Раз. Ого. Раз. So, hello everyone, my name is Artyom, and today I'm going to present you the IGLU competition, which was accepted at competition track of NeurIPS 2021. I hope you can hear me well. So, this competition is organized in collaboration with Microsoft Research, University of Amsterdam, Moscow Institute of Physics and Technology, and Facebook AI Research. So without going in details into the motivation behind this competition, I hope you guys all have played Minecraft, so I don't need to introduce you to the Minecraft. So this task represents a collaborative collaboration, the problem of collaboration between two agents. First one is called the architect. The goal of the architect is to properly instruct the second one, which is called the builder. And the architect is actually has access to the so-called target structure. The target structure is just a set of blocks, which you can see here. And as I said, the architect should properly instruct the builder how to build the target structure. On the other hand, the builder doesn't have the access to the target structure, but instead the builder has access to the chat, and it can, for example, ask clarifying questions from here. And the goal of the builder is to accurately build the corresponding target structure. So actually, in this competition, there will be primarily there will be two tasks, the architect task and the builder task. And I will not go into the details about the first one because this talk is only devoted to the builder task. So particularly, we will be talking about the silent builder task. In this task, we restrict our builder agent to be able to only build. It cannot ask clarifying question, which makes the problem a bit easier. So what happens here? We have a flat world with a few blocks marked white, and these blocks indicate the building zone, so-called building zone. And in that building zone, the builder can actually place blocks to build some sort of structures. So generally, the goal is to build target structure given human instruction. For example, in this row of images, you can see examples of actual targets from the data set, which was collected in a recent work mentioned here. For example, this structure is called a broken heart. So builder is able to navigate, place, break blocks inside of the environment, as well as select blocks of different types. So initially, I will go briefly through the observation and action space. I will talk about how we calculate the rewards, and then I will give you an example of how you can write the code to learn to interact with our environment. So first component of our observation space is 64 by 64 RGB first-person view image. Actually, the examples of these images are rendered at a bit higher resolution are presented here. But in the real environment, you will have access only to 64 by 64 image. The next component is the inverter state. The builder has access to 6 types of blocks, and initially it has 20 blocks of each type. Another component is a chat. So, as I said, in a recent work, there is a collected data set with human-human interaction. One of them was the architect, another was the builder, and they collaborated through the chat interaction and the building process. So in their data set there is chats and the corresponding target structure, so we can use such chats to define goals for our builder. For example, in this image you can see the example conversation between the architect and the builder. So your builder can have access to this kind of chat. Also, we expose to your builder, to your agent, two additional components, which are somewhat special, but I will talk about it a bit later. So these components are first position, described as 5 numbers x, y, z position, and pitch and yaw angles. Yes, 2 angles corresponding to vertical and horizontal direction of the agent. So another component is the grid world state. So as I said, there is a so-called building zone, which is simply a 3D voxel grid world, and each cell of such grid world can be either occupied or free. So if it's occupied, there is a type sort of block in there. So we expose that information to your agent, and that was about the observation. That was about the observation space, and after that goes the action space. Actually, your builder can move across the building zone. There are 3 types of movements. I will describe it later. So just keep in mind that it can just move itself. Another component of the action space is the camera movement. So we expose to you the 2-dimensional continuous control vector through which you can control the camera of your agent. As I said, your agent is able to place and break blocks as well as select blocks of different types. So probably the most important and interesting thing about this competition and our environment is the rewards, is how we calculate the rewards. So the one special thing about the reward is that we don't calculate the reward in just an obvious way. We invented some sort of special function that calculates the reward. So, for example, let's see the image at the right of the slide. So, for example, let's say we have a target structure like this, sort of L-shaped structure, and the agent has built the same structure but in the wrong place. One can say that the agent was successful, but using the naive reward function, the agent would get all negative rewards at each step of environment interaction. So this initially motivated us to bring the invariance to the translations and rotations between the target structure and the one built so far. So unfortunately, this introduces a bit of bias to the training process. However, on the other hand, it makes the task more accessible to the reinforced learning agent. By the bias, I mean that the architect should instruct the builder in a way that is also agnostic to the concrete placement of the target structure. So let's see how we bring sort of environments to the placement, to the translations and rotations around the between the target and build structure. First of all, we compare all relative translations and rotations. Rotations, I mean, around the vertical axis, and we calculate the size of maximal intersections among each translation and each rotations. So, for example, let's see to the image at the right. For example, we have the same target structure, sort of L-shaped target structure, and the agent has built these 2 diagonal blocks. if we naively overlap them, we will see that there is no intersection between them, so anyway the reward will be 0. But if we consider this type of, for example, spatial interaction between the target and the built structures, we will see that the agent has actually built the target structure by half, which means that the agent is halfway to the target. So how we calculate this reward function? First of all, we compare our maximal intersection size among all translations and annotations. We compare that one with the one at the previous time step. And if the maximal intersection size is increased, we reward the agent with +2. If the maximal intersection size is decreased, we reward the agent with -2. If the maximal intersection size isn't changed, we reward the agent with -1 if the agent has put a block, or with +1 if the agent had removed a block. That's it. So there also exists a number of heuristics to accelerate the reward function, because as you may assume, such kind of considering all relative translations and annotation is actually an expensive operation. So we invented a lot of small heuristics to accelerate that one, but I will not talk about that now. So another feature of our environment is how we reset our environment. So if you dive deeply into the mineral, into how mineral works, you will know that upon the resetting the environment, mineral resets the whole mission, which corresponds to pressing the escape button, exit into the main menu, and then starting the mission again, which takes around 10 seconds to reset, which is a lot for reinforcement learning. But we just, on the other hand, we can avoid doing so. Instead, we can teleport our agent. We can remove all blocks that the agent has built so far, and we can just refill its inventory with initial state of blocks. And that's it. We reset the end, and we spend to resetting just one environment step. So that's how we do. We call this operation a fake reset. It is enabled by default, and we hope that such kind of operation would help you. So let's talk about the baselines. When we developed first version of this environment, we tried to train the agent just to test if our environment is even solvable. And we tried to build that kind of goal structure. It's sort of L-shaped structure which consists of 5 blocks. And what we saw is that the agent is very suboptimal. If you remember, I said that we reward the agent with +2 for increasing the size of targets of correctly built structure. So the both approaches, which I will also describe, so both approaches converge to a reward of 6, which corresponds to just 3 blocks placed correctly, which is not a fully solved task. So we tried to train prioritized dueling DQN and PPO for this task, and we observed the same performance for both of them. So we asked ourselves, why is it so? Why we can solve even the simplest task? And the answer is that we were using the wrong backend. By backend, I mean the thing between our agent and the Minecraft itself. We were using the, I would say, naked Malmo, and after that we transitioned to the mineral backend. You may ask, so why is it so? Because mineral is just using Malmo, so why is it so? Well, actually, this is because mineral interacts with Malmo in a very intelligent way. Mineral developers did very brilliant work developing and debugging Malmo and fixing all bugs which were in Malmo. So when we just substituted the backend, we observed that the agent can now fully solve the task, which was win for us. So let's talk about the more recent baseline. And for that baseline, as I said, we have to solve not just one task. We have to build not just one structure, but a set of structures. And each structure is conditioned on the goal, which is represented as a chat. So our policy is accepting not just the state of the world, but the goal represented as a chat. So let's see how we approach that problem, that full problem of silent builder in our baseline. First of all, we split this problem into two sub-problems. The first one is capable of solving by a supervised learning algorithm, and the second one is capable of solving by reinforced learning algorithm. So first one, to solve the first one, we can just train a supervised model that predicts the 3D grid world by the chat. And this is like understandable problem. We can just take some sort of transformer, fine-tune it on our data set, and that's it. And for the second task, so you may assume why try to use such sort of intermediate representation? Why not to just train the agent on the texts or on sort of embeddings? Well, the answer is that by splitting the task into two subtasks in such a way, we can enable reinforcement learning conditioned on a randomly generated subtasks. So now we no longer need the data to learn our reinforcement learning agent. We only need to get somewhere the target structure, no matter how it was obtained. So let's talk about how we will evaluate your solution when you will submit them. First of all, so I will not talk about the online evaluation. So during offline evaluation, we will just calculate sort of metrics that reflect the performance of your agent. For example, we will calculate the reward function. We will calculate the fraction of fully built structures, how many structures your agent has built fully. Also, we will calculate the average completion rate, how far your agent was at building the fraction of, it's just the size of structure built correctly divided by the size of full structure. And of course, the average episode reward. So as I said a bit earlier, we will not expose these two components to your agent during evaluation. So you are free to use them only like with your toy experiments or with your toy experiments, or somehow use that kind of trained model that uses this kind of observation components to train another model, etc. So just be aware that we will not expose this kind of components of the observation space to your agent. So your agent will see only POV image, chat, and inventory. We are happy to announce that all registered participants will be granted with Azure compute power to train their models. Also, we will provide a mentorship session and discussion platform. There will be money prizes. I'm talking about the main NeurIPS competition track. So if you are interested in this competition, please stay tuned at our Twitter account, subscribe to our website, and also if you are wondering at whom to give a credit, here are the organizing team. As I said, the competition is organized in collaboration with Microsoft Research, University of Amsterdam, Moscow Institute of Physics and Technology, and Facebook AI. Below you can see the contributions of each of our teams. That was the first part of this presentation. So if you have any questions, you are free to ask them now. So it looks like there is no questions, which means that I can proceed to the second part of my talk. And now I think I will show you the code. So first of the question? Okay, so I will show you the code. So first of all, in order to run the MineRL, you need to install the Java, the 8th version of Java, and the tool which is called the XVFB. It is literally a sort of virtual display that would allow you to run the Minecraft. So many of you may encounter the problem, then you just install that kind of 8th version of Java, and you try to run your environment, and it will fail. That's because you're not set the 8th version of Java as default, and using this command, the update alternatives, it's a default tool in Ubuntu. You can just set a different version of Java as default. So now I'm going to choose the second version of Java as default. And then make sure that you are using the proper version of Java. So now I will try to install the latest version of the IGLU environment. Actually, I'm sorry, I forgot to do this prior to the talk, so I think we will have to wait for like 3 or 4 minutes until it will be installed. So for those of you who are interested in what the question was if there is the public link to the this notebook. Unfortunately, not yet. But after the talk, I will upload the this iPad notebook to the repository. Thank you for another question. The question was, do we plan to move to another platform such as Windows or OS X? Well, actually, we have to discuss it, but this is definitely planned. Yes, it is still installing. The reason it takes so much time is that during the installation process, it actually compiles the whole Minecraft. Well, thank you for the question. For those of you who are in the Zoom, the question was, are we allowed to use something else except the data that you provide to obtain the solution? And the answer, I think, yes. You are free to use anything possible, unless you are planning to publish it. You will be forced, if yes, you will be forced to make it public. So as I see, now it's been installed, and once I import the IGLU package, it's just been downloading into some sort of path. It just downloads the dataset, which weighs up to 300 of megabytes, and then I need to install the virtual display into the Colab in order to run the Minecraft environment. So we have everything installed. So let's create the environment. The interpreter said that the environment have created successfully. So let's see which action space we expose to the participants. So this action space is essentially the same as that in mineral competition. Your agent can do attack. The attack action just breaks the block which stands before the agent. It can go back. It can move its camera. It can go forward. it can select the proper block stack from the hotbar. Hotbar is just the inventory. It can jump, it can go left, right, and place block. To place block, you should make use action. So as I said, we have agent position in the observation space. The agent position is just 5-dimensional vector, x, y, z, and pitch and yaw angles. The agent has access to the chat. The agent actually has access to the compass. I forgot to mention that, I'm sorry. But we expose the compass observation component because the building zone is essentially the same no matter which direction you are looking at currently. So this is why we expose the compass component. Actually, the agent, I think people experience problem with seeing the observation space. So I'm gonna open the documentation because there is a bit better rendered. So we have access to the grid, as I said, to the compass, to the agent position, to the inventory, and the POV image. So now I'm going to reset the environment, and reset is the operation that is also taking a lot of time, because during the first reset, when you first launch the script, during the first reset, it actually launches Minecraft and starts the mission. But the consecutive reset operations would be much faster because we are doing the fake reset operation. So we reset the env, and let's see, oops. This is a known problem, and this is because I updated the IPython while I was installing the environment, and I think I need to rerun these kind of cells. So please be patient because I'm gonna reset the environment again. Thank you, a great question. So for those who are in Zoom, the question was why the coordinates obtained after the resetting are integer. Will they be integer all the time? And the answer is no, but it depends on the type of movement, which I also describe a bit later, so please be patient. So here is the, I can actually show you some sort of animation. So here what the agent actually observes during the reinforcement learning episode. So as you can see, it just can build some kind of stuff. And at the end of the episode, it reaches the total reward of -7. Let's see what this value is comprised of. So if we access the grid component of our observation space, we will see that actually the size, the amount of placed block is just different from the total reward. This is because some of these blocks are placed correctly. The environment recognizes these blocks as correctly placed. And so let me think how it should be. So I think it is sort of a positive gap between the reward which would be if we would reward all placing block action with -1, so it would be -13 then. But we got -7 just because the agent had placed few of these blocks just correctly. So as I said, we expose some sort of components of the observation space, and the chat is just one of them. So the chat is the main thing that describes the current goal of the agent. I can increase the size if you can see. So in this task, the builder was forced to build some sort of table. So to get started, we need to place 4 orange blocks, the corners of 3 by 3 squares, and then on the second level of the structure consists wholly of red blocks, so some sort of table with orange legs and the red bulk. So as I said, we have 64 by 64 images, 5-dimensional agent position vector, 6-dimensional inventory state, and 9 by 11 by 11 grid world state. Let's look at the agent position. These 3 first components are the coordinates: the x coordinate, the y coordinate, and the z coordinate. This is the pitch angle. The -90 corresponds to looking at the bottom, I think. No. It's a vertical angle, and the last one corresponds to the horizontal angle, which is the yaw angle. So this is basically the inventory state. We have blue, red, orange, green, yellow, and purple blocks. I think I messed up the order a bit, but it's not that important. And also you can cheat a bit and have access to the target grid, which describes the current task. So as I said, we have baseline version 1, in which we split the task into actually 2 subtasks. So first subtask is the supervised learning problem, and the second one is the reinforced learning problem. So here is how we can obtain the how we can get the access to the to that kind of target grid. And here it's obvious, it's easy to see that there is a table with legs marked by 4 and with the bulk marked by 6. But there is a sort of hole at the center of the table, so it's not that good. So let's measure the speed of our environment. As we are working in the Google Colab, it's not that high, but you can expect that it would be much higher in on your working machines, and you will see then then we reach the end of the episode that the next reset operation would be just instant. So here it is. So the next part, which I'm going to talk about, is the selection of the movement types. So the good story is that you are free to choose from 3 types of movement spaces. The first one is discrete movement commands, the second one is continuous, and the third one is human level movement. But I think I'm going to transition to the documentation because it's better rendered here. So as I said, using human actions, you can bring the human control prior to your agent and just control your agent as humans do. I described that kind of action space before. And with discrete actions just mean that your agent goes over discrete positions within the grid world. For example, you can move your agent, and the movement action has 3 possible values. The 0 value corresponds to standing still. The 1 corresponds, if I remember correctly, to the movement forward, and the 2 corresponds to movement backward. Strophe action corresponds to just a movement forward and backward, but to the left and to the right. The jump action just tells the environment that whether should we jump or not in that step. And that's basically it. The rest of the observation space is the same as in the previous one. And the third type of the movement action is continuous movement actions, in which you can move your agent by an arbitrary vector in 3D space. And the special thing about this type of movement is that you are free to fly freely in the building zone. So this is sort of most general one. No. Yes, it's just in the creative mode. And finally, I would like to talk about the tasks in our environment. So, as I said, our environment is parameterized by the goal which the agent is currently pursuing. Each goal is described by a chat and the target structure that is needed to be built. And you can basically tell the environment which set of tasks you want to set to your agent. By default, your agent would pursue just one task. It's called C8, and this is the aforementioned table with a hole, and you can control. Yes, that's the chat we have seen before, and you can control the set of tasks like this. You can import the class which called task set and call the update task set method on your environment, passing to this method the task set object where you specify the preset of tasks which your agent will be pursuing. So after I run this cell, I will see that the task set of the environment is just updated. Another cool thing is that you can basically build your custom tasks, and it is extremely cheap to create a new task. For example, here I am creating a custom task in which the agent has to build 3 blue blocks on top of each other. In the target grid, they are placed at the center of the building zone, but as you may guess, the agent can build them anywhere. In this line, I'm telling that in the custom grid there will be 3 blue colors. Their ID is 1, and I'm filling the 3 values of this tensor. And I call the update task set with custom task object. I provide the fake conversation which I have written myself, and the custom grid. After that, I call the reset operation, and the environment makes this set of 1 custom task active. So you can see that the chat is representing our current task. Another thing is that we can set just random tasks as goals, but these tasks are a bit restrictive because in each of these tasks there will be no chat, so you can only use the rewards and the randomly generated target structures. So let's see what we got. We got a set of random tasks. They are parameterized by maximal number of blocks, which can be in the generated task. Maximum, the highest level inside of the grid world occupied by these blocks. This flag is telling that there can't be blocks which are floating like in the air. So under each block there should be another block. This argument is telling that the maximum distance between any two blocks shouldn't exceed 5. And this one is telling that there can be at most 3 colors. The last argument is used to cache generated tasks. So you can, for example, generate 10 tasks and reuse them, or you can regenerate new task for each reset of the environment. So sometimes it's useful to just generate sort of finite set of random tasks and train your agent on them. So this is just an example of randomly generated task. As I said, there will be just one level of height, and the task is laying on the ground. So I think that's all. Let's close the environment and proceed to the questions. Thank you. Could you please speak a bit louder? Yes, that is a fair observation. So the question was that documentation is actually telling that the fourth component of the the fourth component of the agent position observation component ranges from 0 to 360. So that's why it's not a pitch, it's yaw. That's a fair observation, but I think it's my bad. And I think I will fix that. Thank you. Can anyone please look at the question inside the Zoom, because I cannot open the Q&A panel.
Sorry. While Roman looking for chat questions, I have another question about what is the simplest setup for us to kind of play with, to start with? I mean, should I start from random tasks without chat, and what do you suggest?
Well, thank you for the question. Generally, I would suggest just to take 3 components. First one is the agent position, second one is the current grid observation, and the third one is the target grid observation. You need to concatenate those 3 together, obtaining just a wide vector, and just use it as a state, and parameterize your environment with just one task, no matter which task it will be.
Okay, thank you.
I'm sorry, I cannot open the Q&A panel, but I see that there is... yes, I see the questions. So the first question is, will you be sharing the baseline implementations? Yes, I think we will be sharing the baseline implementations, but please be patient and wait a bit. If you are very urgent to start solving the environment, I suggest you to subscribe to our Twitter account and wait for official announcements. How to submit to LB? How to submit to leaderboard, I suppose the question was. So we have the leaderboard on Coda Lab, and we expect it to be working by the end of this week. We are working very hard to make it possible, so expect by, I think, Monday or Tuesday the announcement. So I think that's all for... one more question.
The last question from me. I didn't get how to create a block with specific color.
So to create the block with specific color...
Have specific action for color, am I right?
So basically you just need to perform an action of hotbar selection. Here it is. This is discrete. It has discrete action space with 7 possible values. The first one corresponds to doing nothing, and the rest 6 of them corresponds to selection of specific colors of blocks. So you have to first perform selection of block of specific type, and then you have to do use action to just place the block.
Okay, and do I need to attack then?
If you want to break it immediately after, then yes.
Oh, yeah, okay. Thank you.
So, thank you.
Okay. Do you have a expert, like expert database or something?
You mean
like
you
that?
mean
Yes.
the data set of demonstrations?
Yes, yes.
So as I said, there is a number of teams that are taking part in the organizing the whole competition, and we have a Facebook AI research team, and this team is working hard currently on the data collection platform. They are almost done with that, so expect the publishing of the data set also.
Okay, thank you.
So thank you everyone for attending. I hope you will enjoy this competition. Thank you. Bye-bye.